Welcome to Cosmic Analysis, where PSR J2322-2650b opens a carbon world around stellar death itself. Before the planet appears, the scene narrows toward a clock-like remnant, holding impossible gravity. A planet survives a dead star orbiting so close that every year lasts hours. It first appears through timing as a hidden tug disturbing a millisecond pulsar's rhythm. That rhythm leads deeper from an unseen companion toward the engine that controls everything. A pulsar is a neutron star small as a city, yet spinning with brutal precision. Before Webb, such a companion seemed destined to fit old categories or vanish chemically. The orbit tightens the mystery, turning survival into a question of constant physical forcing. Radiation, wind, and tides sculpt the planet, while its atmosphere answers every orbit dynamically. Among thousands of exoplanets, this hot Jupiter-like pulsar world remains almost alone in category. Its rarity sharpens the origin problem before any simple story can settle comfortably. Normal survival fails, and ordinary stripping also struggles against the carbon-rich, oxygen-poor evidence. The remaining birth stories circle erosion, transformation, and stranger evolutionary paths still unresolved. The chemistry now becomes the doorway, because carbon is the clue that refuses familiarity. Molecular carbon signals a regime unlike ordinary hot Jupiters, with oxygen and nitrogen strangely scarce. Webb reads the darkness through infrared changes, turning orbital light into atmospheric evidence. Better data does not close the case. It gives the remaining mystery sharper edges. Origin composition and atmospheric maintenance remain uncertain beneath strong winds and extreme carbon ratios. Future spectroscopy and models may decide whether this anomaly hides a larger dead star population. The implication widens. Quietly, planetary evolution can continue after stellar death reshapes everything. The word planet remains, but its meaning bends around remnants, radiation, and alien chemistry. PSR J2322-2650b survives as a measured mystery, real enough to see, strange enough to question. Please like, subscribe, and thank you for listening. Now the dead star's grip begins here. A planet is circling a dead star so closely that its entire year passes in less than a single Earth night. The world is called PSR J2322-2650b, and it moves around a millisecond pulsar, a neutron star spinning once every few thousandths of a second. At first, the idea sounds almost orderly, a small body orbiting a compact star held in place by gravity, following a path that can be measured. But the calm geometry hides a harsher truth. This is a planet living beside a stellar corpse, inside a region shaped by radiation, tidal force, and a kind of gravity that makes ordinary planetary instincts feel unreliable. The star at the center is not shining like the sun. It is the compressed remnant of a massive star that once burned, collapsed, and left behind an object so dense that familiar matter has been forced into a stranger state. Its beams sweep through space with clock-like precision. From far away, they appear as pulses, brief flashes in the dark, as if the star is still marking time after death. That is the first tension in this story. The star is dead, but the system is not quiet. Around it, close enough to complete an orbit in about 8 hours, PSR J2322-2650b continues to move. It is often described as Jupiter mass, Yet almost nothing about its setting feels like Jupiter. There is no broad sunlit distance, no slow majestic orbit, no familiar giant planet drifting through a relatively gentle outer system. This world travels close to a pulsar, near enough that the heavier remnant pulls on it with severe tides. In artist interpretations, the planet is not shown as a perfect sphere, but stretched into a strange lemon-like shape, elongated by the gravitational imbalance between its near side and far side. The image is quiet. The implication is not. A planet, in the usual imagination, is a place that belongs to a star. It forms from leftover gas and dust. It settles into an orbit. It may cool, evolve, lose an atmosphere, gain one, migrate inward, or be battered by collisions. But the parent star usually remains the center of a long, stable story. PSR J2322-2650b asks for a different kind of story because its star has already passed through catastrophe. A neutron star does not appear gently. It is born when a massive star can no longer support its core. The outer layers are thrown away, and the remaining core collapses into an object only city-sized, but with a mass comparable to the Sun. If that remnant spins rapidly and beams radiation from its magnetic regions, astronomers call it a pulsar. If it spins in milliseconds, it becomes one of the most precise natural clocks in the universe. That precision is how such systems first become visible as measurements. A pulsar is not seen only as an object. It is heard in a scientific sense as rhythm. Its pulses arrive at radio telescopes with extraordinary regularity, and when that rhythm shifts even slightly, the motion of an unseen companion can be inferred. PSR J2322-2650b began as that kind of clue, not as a planet photographed like a marble against black space. Its existence was written into timing, into the tiny wobble of a dead star's pulse train. The clue was small, but not empty. Then came the deeper surprise. With Webb, astronomers could study the planet's infrared light across its orbit, not by resolving it as a crisp globe, but by reading the spectrum that changes as the system turns. That spectrum suggested something unfamiliar, an atmosphere rich in helium and carbon, with molecular carbon appearing where ordinary exoplanet chemistry would expect other molecules to dominate. Water methane and carbon dioxide are familiar characters in many atmospheric stories. Here the chemistry points somewhere else. Carbon becomes central. Oxygen and nitrogen appear strangely scarce. The result is not a claim of habitability, and it is not proof of any unknown physics. It is a sharper kind of mystery, quieter and more durable. A planet-sized object near a pulsar seems to carry an atmosphere unlike the atmospheres scientists know how to explain comfortably. This is where the familiar word planet begins to bend. The object is still a planet by the practical rules astronomers use. It is below the mass where deuterium fusion would make it something more like a brown dwarf, and it orbits a stellar remnant. But the word carries expectations, and PSR J2322-2650b resists them. It does not orbit a warm main sequence star. It does not sit in a mild planetary neighborhood. It may have been stripped, heated, reshaped, or altered through a history that is still not clear. It may be a survivor. It may be a remnant. It may be something transformed so thoroughly that its origin is hidden beneath the chemistry Webb now detects. The first answer is simple. It orbits because gravity still works after stellar death. A neutron star, however strange, still has mass. A body near it can follow an orbit just as moons orbit planets and planets orbit stars. But that answer is incomplete because survival is not the same as explanation. The question is not only how PSR J2322-2650b can move around the pulsar today. The deeper question is how it arrived at this state, how it kept or acquired such an atmosphere, and why that atmosphere appears so dominated by carbon in a place where the environment should be brutally selective. The measurement does not solve the story. It sharpens it. A dead star still holds a world in its grip, and the world is not behaving like the planetary categories built from quieter systems. The orbit says the body is there. The shape says the tides are severe. The spectrum says the air, if that word can be used for such a furnace, belongs to a chemical regime that has barely been explored. Each clue answers one question and opens another. The planet exists. The star is dead. The atmosphere is strange. And the next step is to listen to the clock at the center. Because before Webb could read the carbon world's atmosphere, astronomers first had to notice the tiny disturbance it made in the rhythm of a spinning corpse. The first sign of PSR J2322-2650b was not a picture of a world. It was a disturbance in time. A pulsar is one of the universe's most disciplined clocks, not because it was built for order, but because its violence has become regular. As the neutron star spins, beams of radiation sweep outward from regions near its magnetic poles. If one of those beams crosses Earth radio telescopes receive a pulse, then another, then another. For an isolated pulsar, the pulses can arrive with such precision that the star seems to beat like a metronome in deep space. But PSR J2322-2650 was not completely alone. Its rhythm carried a small repeating displacement, a motion hidden inside the clockwork. Something was tugging it, something close, something moving around it in only 7.75 hours. That is where the planet first entered the story, not as a surface, not as a cloud layer, not as a glowing crescent, but as a gravitational signature inside the timing of a dead star. The clue is almost too small to feel. From Earth, the pulsar is a point source far beyond any direct view of a companion wrapped close to it. The body near it does not announce itself by shining like a star. It does not cross a bright solar disk in the exoplanet transit picture. Instead, the companion makes the pulsar move, and that motion changes the distance between the pulsar and Earth by tiny amounts during the orbit. When the pulsar is moving slightly toward us, its pulses arrive a little earlier. When it is moving slightly away, they arrive a little later. The difference is not dramatic in human terms, but in pulsar timing, tiny delays become evidence. A clock that accurate can turn a nearly invisible companion into a measured orbit. This is the quiet genius of the method. It does not need a photograph. It needs patience, repeated measurements, and trust that gravity leaves patterns even when light gives almost nothing. The original timing work identified the system as a binary millisecond pulsar. The pulsar spins once in 3.5 milliseconds so fast that 1 second contains hundreds of rotations. Its companion appeared to have a planetary mass on the scale of Jupiter, and it followed a nearly circular path around the remnant in less than 8 hours. The orbit was not wide and relaxed. It was tight, intimate by astronomical standards, with the companion locked into a region where the pulsar's gravity and radiation could not be treated as background scenery. The measurement was clear enough to say that this was not a distant outer planet drifting around a dim remnant. It was a close companion tied to the pulsar's own motion. The meaning was harder. In ordinary exoplanet discovery, a planet usually reveals itself through the effect it has on a living star. It dims the star during a transit, or pulls the star back and forth through radial velocity, or appears indirectly through microlensing, or rarely, is imaged as a faint dot separated from the host. Pulsar planets belong to a colder category. They are detected through time itself, through the way an ultra-stable signal refuses to arrive exactly when it would if the pulsar were alone. The planet becomes a correction to a clock. The orbit becomes a repeated delay. The companion is measured before it is imagined. That reversal matters because it keeps the story disciplined. The data does not begin with a cinematic world. It begins with the strict question, what kind of mass in what kind of orbit would produce this timing pattern? Once that question is answered, the world can be given a name, but the name does not remove the mystery. PSR J2322-2650b may be called a planet, yet it orbits a host unlike the stars that shape most known planets. Its year is short enough to fit between dusk and dawn on Earth. Its sky, if described from within the system, would not be lit by a normal sun. The central object would be small in size, but immense in density with radiation beams and high-energy particles defining the environment more than steady visible warmth. This is where a measurement becomes a landscape. The pulse timing gives the orbit. The orbit gives the proximity. The proximity gives the first hint of the physics acting on the planet. A companion moving that close to a neutron star cannot be understood only as a point mass. It must be considered as matter under stress, heated from one side, pulled out of shape, and exposed to the wind of a compact remnant. Yet the timing alone could not say what the atmosphere was made of. It could not reveal carbon. It could not show helium. It could not decide whether the body resembled a hot Jupiter, a stripped stellar core, or something in between. It could only say that something was there, circling with astonishing regularity, forcing the pulsar's pulses to carry a trace of orbital motion. That is the micro-payoff of the first measurement. The planet becomes real before it becomes understood. The rhythm proves companionship, but not origin. The clock reveals the orbit, but not the chemistry. The motion tells astronomers that a body survives close to the neutron star, but not how it reached that place or why it looks the way it does. In that gap, the entire mystery begins to widen. Every orbit repeats the same question. If the companion is so close, why has it not been destroyed? If the pulsar has lived through stellar death, what history carried this body through the aftermath? If the timing identifies a planetary mass object, why would later observations find an atmosphere so unlike ordinary giant planets? The first measurement does not answer those questions. It gives them a foundation. It tells where the story stops being speculation and becomes astronomy. There is a clock in the dark. Its rhythm is slightly displaced. The displacement maps an orbit. The orbit belongs to a world. But to understand why that world is so strange, the next step is to look more closely at the clock itself, because a millisecond pulsar is not merely a dead star with a companion. It is one of the most extreme objects a planet could call its sun. A millisecond pulsar is a star reduced to a clock after catastrophe. It is not a star in the ordinary sense, because its long life of nuclear burning has ended. It is not a planet's gentle lamp, because its light does not pour outward as steady warmth. It is the collapsed core left behind after a massive star has exhausted the fuel that once held gravity in balance. When that balance fails, the core falls inward with almost unimaginable force, compressing matter into a neutron star, an object with roughly stellar mass packed into a sphere no larger than a city. The result is small only in size. In every other way, it is excessive. gravity deepens, density becomes extreme. Magnetic fields can become enormous. Rotation can accelerate until the remnant spins with a precision that feels less like weather and more like machinery. PSR J2322-2650 belongs to this family, and its companion moves around not a dim ember, but one of the universe's strangest survivors of stellar collapse. That is why the word orbit is not enough. Many things orbit many other things in space. A moon orbits a planet. A planet orbits a star. Dust orbits a young sun before gathering into larger bodies. But a world orbiting a pulsar is not moving through a familiar planetary neighborhood. It is moving around a compact remnant whose entire surface could fit within a terrestrial city, while its mass bends space as deeply as a normal star's mass would. To imagine the scale, picture the sun compressed until its diameter is no longer wider than a continent, no longer wider than a country, but comparable to the span of a major city. The mass remains. The volume vanishes. Matter is forced into a state where ordinary atomic structure no longer resembles the matter of rocks, oceans, or air. The comparison is imperfect, but it points toward the problem a planet near such an object is close to a gravitational source that is physically tiny, yet dynamically immense. The pulsar's beam adds another layer. The neutron star does not simply sit there as a dark weight. As it rotates, charged particles and radiation are guided by magnetic fields and swept into space. The beam is often compared to a lighthouse, and the comparison is useful if it is kept cold and precise. A lighthouse does not flash because it turns on and off. It flashes because its beam rotates past the observer. A pulsar can appear similar from Earth. The radiation is always being directed through space, but telescopes receive it as pulses only when the beam crosses our line of sight. In PSR J2322-2650, the rotation is measured in milliseconds. Hundreds of times in a single second, the remnant turns. The planet nearby is not watching a sunrise and sunset in any ordinary sense. It is moving through the domain of a spinning magnetic engine. This is where the old planetary intuition begins to fail. The sun is large in the sky of Earth because Earth is close enough to receive its warmth, but far enough to orbit safely over billions of years. The sun's radiation is strong, yet it has a broad and steady character that life and climate can respond to. A pulsar is different. It can send high-energy particles and beams through the system, and although the details depend on the geometry, the environment around it is not a mild extension of sunlight. It is a place where radiation pressure, particle winds, magnetic structure, and tidal gravity may all matter. For PSR J2322-2650b, this matters because the planet is extremely close. Its orbit is not measured in years or months or even days. It is measured in hours. The short orbit means the companion repeatedly presents itself to the pulsar's influence with a speed and intimacy that make the system feel compact, compressed, and unstable to the imagination. Yet it persists. That persistence is the quiet contradiction. A neutron star is often described as dead because fusion has stopped, but the word dead can be misleading. Dead does not mean inactive. Dead does not mean gentle. A pulsar is a stellar corpse that still spends rotational energy, still shapes its surroundings, still marks time in beams, still interacts with companions. In some binary systems, a pulsar can pull material from a nearby star or erode a low-mass companion with its wind, creating what astronomers call black widow systems. The name is dramatic, But the physics is careful material transfer can spin up the neutron star, and the energized pulsar can later bombard the companion. PSR J2322-2650b sits near that conceptual territory, but not cleanly inside a simple version of it. The host is a millisecond pulsar. The companion is officially planetary. The orbit is tight. The chemistry, as Webb later suggested, is not what the easiest stripped companion story would predict. This means the pulsar is not only background, it is part of the origin question. If the companion formed before the stellar death, it had to survive events that should have been destructive. If it formed after, then the system needed a reservoir of material and a pathway for building a planet around a compact remnant. If it began as something larger and was stripped down, then the remaining body must explain why its atmosphere appears so carbon-rich and so deficient in other common elements. Every route passes through the pulsar's history. Every route is difficult. The micro payoff is clear but incomplete. PSR J2322-2650b is strange because its host is not merely a small star. It is a collapsed remnant whose mass rotation, radiation, and magnetic environment redefine what closeness means. A planet near a normal star can be hot. A planet near a pulsar can be forced into a category where heat is only one part of the story. The orbit is a clock, but the host is also a furnace of particles, a gravitational point of stress, and a remnant of an explosion. To understand the planet, the listener must first understand that the word dead star describes a beginning, not an ending. The next problem is sharper. If astronomers once had an older model for what such companions should be, why did PSR J2322-2650b refuse to stay inside it? The older expectation was not foolish. It was simply built from a smaller set of possibilities. Before Webb turned PSR J2322-2650b into an atmospheric puzzle, the system could be placed near a known family of strange binaries, millisecond pulsars with very low-mass companions, sometimes shaped by long histories of mass transfer and erosion. In that picture, the companion begins as something larger and more star-like. Material flows toward the neutron star. The neutron star spins faster. Later, the energized pulsar wind and radiation bombard the remaining companion, peeling it down, heating it, and leaving behind a compact survivor. The idea is severe, but it has logic. A star can be reduced. A companion can be stripped. A pulsar can become a fast clock through the very act of feeding. At first, PSR J2322-2650b seemed as if it might belong somewhere in that landscape. It was close. It was low in mass compared with stars. It orbited a millisecond pulsar. The visible outline of the story appeared to fit. Then the chemistry arrived, and the old frame began to bend. The problem was not that a companion could exist near a pulsar. Astronomers already knew that some pulsars have companions, and a few have planetary mass bodies. The problem was what this companion seemed to be made of, or at least what its atmosphere appeared to reveal. Webb's spectrum did not look like the familiar atmosphere of a hot Jupiter around an ordinary star. It did not simply show the usual expected molecules in a more extreme setting. Instead, it pointed toward helium and carbon, with molecular carbon becoming a major clue. In many planetary atmospheres, carbon tends to hide inside compounds, such as carbon monoxide, carbon dioxide, or methane, depending on temperature and chemistry. Here, the signal suggested carbon in forms that normally should not dominate unless oxygen and nitrogen are unusually scarce. That is the pressure point. A stripped star should not easily leave behind an atmosphere that looks so selectively carbon-rich. If the object were merely the exposed remains of a companion, the chemistry would be expected to carry a broader elemental memory of the original body. Stars are not made of pure carbon. Their interiors are layered, processed, and complex, but they do not naturally hand astronomers a simple carbon and helium answer. Nuclear physics makes heavier elements in particular stages and places, and stellar material contains mixtures. So when a planet-sized companion near a pulsar appears dominated by carbon-bearing molecules, the question is no longer just how much mass was lost. It becomes what kind of history could remove hide or avoid so much oxygen and nitrogen while allowing carbon to speak so loudly. The measurement is clear enough to be provocative. The meaning is harder. This is where the old model does not collapse completely, but it loses its clean shape. A black widow-like story can still explain parts of the system, the close orbit, the possibility of erosion, the relation between a fast pulsar and a smaller companion. But it does not comfortably explain the whole atmosphere. A normal hot Jupiter story also struggles. Hot Jupiters are large gaseous planets that orbit very close to living stars, often heated until their atmospheres glow in infrared light. PSR J2322-2650b resembles that family in some physical impressions such as mass and intense heating, but its host is not a sun-like star, and its chemistry is not behaving like a familiar hot Jupiter atmosphere. It is as if two known categories overlap only at their edges. One gives the orbit, another gives the size. Neither gives the full chemical answer. Imagine finding an ancient book in a burned library. Its cover looks familiar. Its size fits the shelf. Its binding suggests it belongs to a known collection. But when opened, the pages are written in a language that should not be there. The object can still be catalogued, yet the catalogue no longer explains it. PSR J2322-2650b creates a similar scientific discomfort. Its orbit says pulsar companion. Its mass suggests a giant planet. Its atmosphere says something else has happened. The label remains useful, but it no longer carries enough meaning. The contradiction is made sharper by the system's closeness. At roughly 1 million miles from the pulsar, the planet is not an untouched relic sitting far from danger. It is forced by the environment every orbit. Its day side may be heated intensely. Its night side may be cooler, but still part of a violently redistributed atmosphere. Tides pull the world away from a simple spherical shape. Winds may move heat and material around the planet in ways unlike the circulation of ordinary gas giants. If carbon-rich material is being lifted, mixed, crystallized, or exposed, the atmosphere is not merely a static chemical sample. It is a moving answer. But that motion makes the origin problem harder, not easier. An atmosphere can change with time. It can be stripped, replenished, mixed, and irradiated. Yet the process must still explain why the current spectrum looks so unlike the categories that came before it. The micro payoff is that the contradiction has a precise form. PSR J2322-2650b is not mysterious because scientists have no ideas. It is mysterious because the best familiar ideas explain only pieces. The pulsar companion model explains why a small body might be close to a millisecond pulsar. The hot Jupiter comparison explains why an irradiated giant planet might have a glowing atmosphere. The Black Widow analogy explains how a companion might be eroded, but the carbon-rich, helium-rich, oxygen-poor atmosphere resists being folded neatly into any one of them. The planet does not ask science to abandon physics. It asks science to account for details that physics has not yet organized into a satisfying path. That is a quieter kind of drama and a better one. The old model bends because a real spectrum has put weight on it. A world close to a dead star is not just surviving. It is carrying chemical evidence of a past that remains hidden. To go further, the next section has to leave the old categories behind and enter the machinery acting on the planet. Now the radiation, gravity, wind heat, and tidal force that keep reshaping this carbon world every time it circles the pulsar. The machinery around PSR J2322-2650b does not announce itself with fire. It works through forces that are mostly invisible. The planet moves through an environment where gravity is not merely a background rule, but a sculptor, where radiation is not simply light, but pressure heating and particle impact, where wind does not mean air moving across a surface, but streams of energetic particles flowing from a compact remnant. At first, the system can be imagined as a planet circling a small star. That image is useful only for a moment. The pulsar is small in size, but not small in mass. Its gravitational reach is severe, and the companion is so close that the difference between the pull on the near side and the far side becomes physically important. Tides stretch the planet. They do not need to tear it apart to matter. They only need to deform it, heat it, and keep its atmosphere in a state that cannot be understood as calm. This is the first hidden mechanism. Proximity changes the meaning of survival. A planet can survive an orbit and still be permanently stressed by it. The orbit of PSR J2322-2650b is short enough that the same drama repeats again and again within hours. One side faces stronger irradiation. The atmosphere absorbs energy. Heat tries to move. Winds respond. The planet's shape is pulled away from roundness, as though gravity has turned it into a body with direction, a world whose outline remembers where the pulsar is. The effect is not just visual. A stretched planet has different pressure patterns, different circulation possibilities, and different ways for gases to move between day and night. On Earth, weather feels large because winds can carry storms across oceans and continents. On this world, the scale is harsher. The atmosphere may be racing around an object under intense external forcing, with high temperatures, rapid rotation, and constant exposure to a pulsar's energetic environment. The air is not a quiet blanket. It is a moving laboratory. The radiation matters because a pulsar does not warm like a normal star. Ordinary planets around ordinary stars receive a broad stream of visible and infrared light, along with ultraviolet radiation and charged particles. A pulsar can add a different mixture, including high-energy particles and beams that arise from its spinning magnetic structure. The details depend on geometry, because a beam only strikes what it crosses, and a wind can interact unevenly with a companion. But the general problem remains. PSR J2322-2650b is not receiving the simple sunlight of a main sequence system. It is receiving energy from a dead star that is still spending rotation, still driving particles, still imposing structure on space around it. That is the hidden turn. The host has stopped burning nuclear fuel, yet it continues to shape the planet more violently than many living stars shape theirs. Heat is only one part of the story. Chemistry is another. In an atmosphere exposed to extreme temperatures and high-energy radiation, molecules can form, break, recombine, and circulate in patterns far from familiar planetary balance. Molecular carbon appearing in the spectrum suggests that carbon is not simply present, but able to survive or be replenished in forms that can leave an infrared signature. That raises a difficult question. If oxygen or nitrogen were abundant in the right forms, carbon would often bind with them, creating more familiar molecules. Instead, the signal points toward a regime where carbon is unusually free to dominate. The planet is therefore not only being heated, it is being chemically sorted or chemically revealed by conditions that may be stripping away some possibilities while preserving others. The evidence does not yet say exactly how. It says where the problem lives. A useful comparison is a shoreline under constant waves. The beach at dawn is not the original arrangement of sand. It is the latest shape made by tide, wind, water, and time. PSR J2322-2650b's atmosphere may be similar in principle, though far more extreme. What Webb reads is not necessarily a pure memory of formation. It may be the present surface of a long process, a chemical shoreline carved by irradiation circulation, gravity, cooling, and loss. Some material may escape, some may settle, some may rise from deeper layers, some may be transformed into species that can exist only because other atoms are scarce. A spectrum, then, is an archive with missing pages. It records the current atmosphere, but the current atmosphere may be the last visible layer of a deeper history. This is why the phrase carbon world must be used carefully. It does not mean a polished black planet made entirely of carbon. It does not confirm diamond rain falling visibly through a sky. It means that the detected atmospheric chemistry appears profoundly carbon-rich compared with what astronomers expect from ordinary exoplanets. That distinction matters because science becomes less trustworthy when a clue is inflated into a certainty. Diamonds may be discussed as a possible consequence of carbon-rich interiors and crystallization under the right conditions, but the atmosphere itself is not a fantasy jewel box. It is evidence of chemistry under pressure. The quieter version is stronger. A planet near a pulsar seems to be showing molecular carbon where the familiar models did not expect it, and that is strange enough without decoration. The micro payoff is this: PSR J2322-2650b is shaped by an active system of forces, not by one dramatic cause. Gravity stretches it. Radiation heats and alters it. Particle winds may erode or energize it. Atmospheric circulation redistributes heat and chemistry. Extreme proximity locks all these processes together so tightly that the planet cannot be treated as an isolated body. Its atmosphere is not simply what the planet has. It is what the planet becomes while orbiting a neutron star. That helps answer why the environment looks so strange, but it opens a larger scale of mystery. If these forces can shape one companion so deeply, then PSR J2322-2650b may not be only a single odd world. It may be a visible example of a broader, mostly hidden population of planets and remnants that survive where stars have already died, waiting for the right clock, the right telescope, and the right spectrum to reveal them. PSR J2322-2650b is strange, partly because it is nearly alone in the catalogue of known worlds. Thousands of exoplanets have been found around ordinary stars, and many of them are strange in familiar ways. Some are gas giants pressed close to their stars until their atmospheres glow. Some are rocky worlds locked into short orbits. Some are cold giants moving far out in darkness. But a Jupiter mass object orbiting a pulsar is not simply another variation on the same theme. It belongs to a narrow and unsettling edge of planetary science where the host star has already died and the companion still remains. That rarity changes the scale of the mystery. A single unusual atmosphere might be a local accident. A single unusual orbit might be an evolutionary leftover. But when both appear together, the system becomes a question about what planets can become after stellar death. The familiar map expands, and its borders begin to blur. Most planets are studied in the context of main sequence stars, the long-lived stellar phase in which hydrogen fusion provides steady energy. That is the environment in which the solar system exists, and it is the environment that shaped much of planetary science. Around such stars, astronomers can compare worlds by size, mass, temperature, orbital distance, density, and atmospheric composition. They can build categories: hot Jupiters, super-Earths, mini-Neptunes, cold giants, lava worlds, temperate terrestrial planets. The categories are imperfect, but they give science a kind of grammar. PSR J2322-2650b interrupts that grammar because its host is not in that long, stable phase. The central object is a neutron star, a remnant. The planet is not just close to an unusual star. It is close to the remains of stellar violence. That makes its current state part of a larger sequence, one that includes collapse, possible mass transfer, spin-up irradiation, and erosion. This is where the scale expands from one orbit to an entire lifetime of matter. A planet does not become strange only in the moment astronomers detect it. It becomes strange through history. If PSR J2322-2650b began as a normal gas giant, then it had to survive a host star's violent transformation or be captured into the system later, and neither route is simple. If it began as a companion star or a stellar remnant stripped down to planetary mass, then its current mass and atmosphere must be explained by removal, heating, and chemical exposure. If it formed after the neutron star appeared, then material must have remained or returned in a disk capable of building a planet around a compact remnant. Each path stretches ordinary assumptions. The object is not only asking what it is asking when it became what it is. The wider pattern is small but important. Pulsar planets are rare but not imaginary. The first confirmed exoplanets were discovered around a pulsar, showing that planets could exist in places far removed from solar system comfort. That discovery already forced astronomers to separate the idea of a planet from the idea of a gentle star. Yet, PSR J2322-2650b adds a different layer, because it is not only detected as a companion, it has an atmosphere that Webb could study. It is not just an orbit in timing data. It is a world with thermal emission, chemistry, circulation, and shape. The planet becomes a bridge between two fields that often feel separate: the precision timing of pulsars and the atmospheric science of exoplanets. One field reads clocks, the other reads light. Here both are needed. That is the larger structure beneath the mystery. A pulsar system is not a miniature solar system with a smaller sun. It is a post-catastrophe environment where matter may have been rearranged by explosion, accretion, tidal force, and long-term radiation. Around ordinary stars, planets usually inherit their compositions from protoplanetary disks. Around pulsars, the inheritance may be broken, recycled, or remade. A companion may be a survivor from before the collapse. It may be a second-generation body formed from fallback material. It may be a remnant of a once larger star that has been stripped almost beyond recognition. The same word planet can cover very different histories. The label describes the present orbit and mass. It does not automatically reveal the past. A human-scale image helps. Imagine a city rebuilt after a fire so complete that almost every street has been erased. Later, someone finds one standing tower, but its stones are not arranged like the city's old architecture. The tower proves that something survived, but it also suggests that survival involved rebuilding, stripping or replacement. PSR J2322-2650b is like that tower in the ruins of a stellar system. It is not enough to say that it is still there. Its presence asks what was destroyed, what remained, and what was transformed into the body Webb now observes. The answer may not be a single event. It may be a sequence. The micro payoff of this wider view is that rarity becomes evidence, not just decoration. PSR J2322-2650b matters because it occupies a place where several scientific maps overlap and fail to align perfectly. It resembles a hot Jupiter in temperature and planetary scale, but not in host star. It resembles a pulsar companion in orbit, but not in atmospheric composition. It resembles a black widow-like system in some evolutionary possibilities, but not in the clean predictions such a picture would prefer. Each resemblance gives partial understanding. Each mismatch keeps the system alive as a problem. So the scale has expanded. The story is no longer one planet close to one dead star. It is a test of how planets' companions, atmospheres, and remnants can persist across stellar death. It suggests that some planetary bodies may not be born once and then simply age. They may be reclassified by catastrophe, carved by radiation, and made legible only after their original context has vanished. But widening the scale also creates a sharper difficulty. If several origins remain possible, the simplest answer should be tested first. And for PSR J2322-2650b, the simplest explanation begins to fail exactly where the atmosphere becomes most specific. The easiest origin story for PSR J2322-2650b begins with survival. Imagine a giant planet forming around a normal star, enduring the star's life, then somehow remaining after the star dies and becomes a neutron star. The picture has a clean appeal because planets are durable things. Some can outlast intense radiation. Some can migrate inward or outward. Some can remain in altered orbits. It seems possible to ask whether PSR J2322-2650b is simply a gas giant that survived too close to the wreckage. But this answer weakens almost as soon as it is touched. A massive star does not become a neutron star quietly. Before collapse, it evolves through enormous changes in size and luminosity. During collapse, the system is shaken by mass loss radiation and violence. Afterward, the remnant may interact with companions through accretion, spin-up, and particle winds. A normal giant planet could survive somewhere perhaps, but survival alone does not explain why this one now orbits so close, so quickly, and with such unusual chemistry. That is the first failure of the easy answer. It explains presence, but not condition. The second easy story begins from the opposite direction. Perhaps the object was never a normal planet. Perhaps it began as a low-mass star or stellar companion, and the pulsar stripped it down until only a planet-mass remnant remained. This picture fits certain parts of the system better. A millisecond pulsar often points to a history of interaction because neutron stars can be spun up when material from a companion falls onto them. Later, the energized pulsar can bombard what remains. In black widow systems, the companion is gradually eroded as if the pulsar is reducing a larger body. That mechanism offers a way to make a small companion in a tight orbit. It provides a physical path, not just a label. But PSR J2322-2650b resists even this answer because the atmosphere does not look like a simple stripped stellar core. It appears too chemically selective. The problem is carbon. Carbon itself is not rare in the universe. It is one of the essential products of stellar evolution, a major element in dust planets' atmospheres and life chemistry. But an atmosphere dominated by molecular carbon in this setting is not the same as saying carbon exists. It means carbon is appearing in forms and amounts that imply the absence, hiding, or removal of other elements that would normally compete with it. Oxygen and nitrogen matter because they give carbon other chemical partners. If they are present in sufficient amounts under the right conditions, carbon will not remain so visibly free. It will bind into more familiar molecules. So the stripped star explanation has to do more than reduce mass. It has to explain how a body that once had a broader elemental mixture could end up presenting such a carbon-rich, helium-rich atmospheric face. This is where the model becomes strained, not impossible. Strained. The third easy answer is to blame the pulsar's environment for everything. Radiation is severe. The orbit is tight. The planet is hot. Winds may be strong. Tides distort the body. Perhaps then the atmosphere is simply what happens when any companion is placed close enough to a neutron star. But this answer also fails to satisfy because harsh environments do not automatically create precise chemistry. Heating a world can change its atmosphere, strip some gases, drive winds, and alter molecules. It does not by itself explain why molecular carbon should dominate so dramatically. Radiation can break compounds, but it must still work with the material available. Tides can deform a planet, but they do not choose elements. Winds can move heat, but movement is not origin. The environment is powerful, but power alone is not explanation. The meaning is harder. A better comparison is a crime scene after a storm. Rain may erase tracks, scatter debris, and change the surface, but it does not create every object found there. To understand the scene, investigators must ask what was already present, what was removed, what was rearranged, and what new marks the storm added. PSR J2322-2650b's atmosphere works in a similar way. The pulsar environment may be the storm, but the carbon-rich spectrum is the evidence left after many processes have acted. Some chemistry may reflect deep interior material. Some may reflect atmospheric escape. Some may reflect circulation between hot and cold regions. Some may reflect crystallization or separation in layers beneath what Webb can infer. None of these possibilities can be treated as final without more testing. The clue is not empty. It is not complete either. This is why the simple answers fail one by one. A normal surviving planet struggles to explain the orbit and atmosphere. A stripped stellar companion struggles to explain the chemical purity implied by the spectrum. A pulsar processing explanation struggles to explain why severe irradiation produces this particular carbon-dominated result, rather than a more familiar altered atmosphere. Each answer carries part of the truth, but each leaves a remainder. That remainder is where the science lives. It is tempting in a story like this to turn the failure of simple models into exaggerated language. To say the planet should not exist. To say physics is broken. To say the universe has made an impossible world. But that would make the mystery smaller, not larger. PSR J2322-2650b does not need false impossibility. It is more interesting because it is possible measured and still difficult. The orbit obeys gravity. The atmosphere obeys chemistry. The pulsar obeys known principles of compact stellar remnants. The difficulty is that the known principles have not yet been arranged into a single history that explains all details at once. The micro payoff is disciplined uncertainty. The planet is not a miracle outside science. It is a problem inside science. The simple explanations fail because the data are too specific. A close orbit is not enough. A planetary mass is not enough. A dead star is not enough. The carbon-rich atmosphere forces the story to include formation stripping, heating circulation, and chemical separation together. That is why the next step cannot be choosing one answer too early. The next step is to set the competing explanations beside one another and ask which parts of the world each one can illuminate and which parts remain in shadow. The competing explanations for PSR J2322-2650b do not line up like clean choices on a list. They overlap, borrow from one another, and fail. One explanation begins with a planet that was already there. A giant world formed around the original star before the star became a neutron star. Another begins with a companion that was once more star-like, then stripped down until it reached planetary mass. A third begins after catastrophe with material left behind or returned to the system, forming something new around the pulsar. Each path has logic. Each path also has a cost. The system is so tight, the host so extreme, and the atmosphere so carbon-rich that no explanation can move forward without stumbling over a detail. That is why the mystery is structured. The first possibility, survival, has the simplicity of an ancient witness. In this picture, the planet formed around the original massive star long before the neutron star existed. It endured the star's violent life, the swelling and mass loss that came before collapse, and the transformation of the core into a compact remnant. If it somehow remained bound, later interactions could have changed its orbit, drawing it inward or leaving it close to the pulsar. Planets can be resilient, and gravity can preserve companions if the geometry allows it. But the weakness is just as obvious. A giant planet sitting this close to a neutron star must explain more than endurance. It must explain why it is there, now, why its year lasts only hours, and why its atmosphere does not resemble a more ordinary gas giant pushed to extremes. Survival gives a beginning. It does not give the chemistry. The second possibility is erosion. Here, PSR J2322-2650b is not a planet that survived as a planet, but the reduced remnant of something larger. In a black, widow-like evolutionary picture, a companion feeds the neutron stars, spinning it up into a millisecond pulsar. Later, the pulsar's wind and radiation attack the companion, stripping mass away. Over immense time, a star can be diminished into an object with planetary mass. This story explains why the orbit can be close and why the system contains a rapidly spinning pulsar. It also gives the environment an active role. The planet is not simply a survivor. It is a body carved down by its host. The difficulty is that carving something down does not automatically make it carbon-rich in the right way. If the companion began as a star, its material should carry a mixture of elements. Stripping can expose deeper layers, but the observed atmosphere still asks why carbon and helium dominate so strongly while oxygen and nitrogen appear so limited. The knife may explain the wound. It does not explain every trace in the blood. The third possibility is second-generation formation. In this version, the planet or planet-like body forms after the neutron star has already been created, perhaps from material left over, ejected, captured, or arranged into a disk through later interaction. This idea is attractive because it does not force a normal planet to survive the full violence of stellar death. Instead, it allows the dead star's aftermath to become a construction site. Around compact remnants, disks of material can exist, and disks are where planets are built. But this pathway also faces a hard question. What material was available? How did it cool and collect? And why would it build a Jupiter mass object so close to a pulsar with such a strange inventory? The formation site changes. The chemical problem remains. There may also be hybrid routes. A body could begin as one kind of companion and end as another. It could lose mass, receive irradiation, undergo internal differentiation, and then reveal deeper carbon-rich layers through atmospheric mixing or escape. Its present spectrum might not record its original composition. It might record the latest visible surface of a long evolutionary sequence. In such a hybrid picture, no single event produces the planet as it appears today. The atmosphere becomes the result of history, not a fingerprint from birth. That makes the science harder, because the same present-day clue can sometimes be reached by different pasts. A carbon-rich signal might mean unusual origin. It might mean unusual processing. It might mean unusual loss. It might mean a combination not yet modeled well. The evidence points toward a problem, not a verdict. A human-scale comparison helps keep the uncertainty honest. Imagine finding a metal object on an ocean floor. It is corroded, bent, and coated with minerals. It might have fallen from a ship formed from wreckage, or been altered so long by saltwater that its original shape is partly erased. To understand it, one must ask not only what it is made of, but what happened to it. PSR J2322-2650b is similar in spirit. The atmosphere is the corroded surface of a deeper story. The planet's present state is not a simple fossil. It is an active remnant under continuing force. This is why scientists must hold the explanations carefully without pretending the most dramatic one is automatically true. The survival story respects the planet label, but struggles with closeness and chemistry. The erosion story respects the pulsar environment, but struggles with the selective carbon signal. The second-generation story respects the post-death setting, but struggles with construction and composition. The hybrid story may be closest to reality, but it spreads the answer across many processes and makes prediction more difficult. The micro payoff is that PSR J2322-2650b is not mysterious because there are no explanations. It is mysterious because every explanation explains something important and leaves something important behind. The competing stories form a map of the unknown. They show which measurements matter next: better spectra, better temperature maps, better circulation models, better timing, and perhaps other pulsar planets for comparison. Until then, the carbon world remains suspended between categories. It may be survivor remnant rebuilt object, or all three across different stages of its life. But to feel the strangeness fully, the next step is to bring the system down to a scale the mind can hold, a year shorter than a workday, a star the size of a city, and a planet stretched by gravity, while its atmosphere carries the chemistry of an unresolved past. To understand PSR J2322-2650b, the scale has to be made small enough to feel even if the system itself refuses to become ordinary. Begin with the year. On Earth, a year is the slow return of seasons, the long sweep of a planet around a warm star. On this world, a year lasts less than 8 hours. A person could fall asleep at night, and before morning, the planet would have completed a full circuit around the dead star at its center. That comparison is not meant to make the world familiar. It does the opposite. It reveals how compressed the system is, how tightly orbit and force are folded together. PSR J2322-2650b is not wandering through a spacious solar system. It is locked into a close passage around a neutron star, moving through the same severe environment again and again, faster than human routine can make sense of. The number is simple. The meaning is not. Now shrink the star. A normal star fills the imagination with size a glowing sphere, immense enough to dominate every planet near it. A neutron star reverses that instinct. It can carry a mass comparable to the Sun, while being only about the size of a city. If such an object could be placed where a city sits, its gravity would not feel like a city. It would feel like a collapsed star compressed into an urban outline, a cosmic mass wearing an impossible scale. The planet orbits that. The host is tiny in diameter, but enormous in gravitational authority. From a human perspective, this is one of the strangest contrasts in astronomy, a dead star small enough to imagine on a map, yet dense enough to pull a Jupiter mass companion into a distorted shape. The image becomes almost quiet because the dimensions are so clean. City-sized star, giant planet, million-mile separation, 8-hour year. Each phrase is understandable. Together, they stop feeling normal. The planet's shape gives another bridge. A gas giant in the imagination is round-layered and symmetrical with bands, storms, and soft limb darkening. PSR J2322-2650b is expected to be stretched by tides, because one side is closer to the neutron star than the other. Gravity does not pull the entire body equally. It pulls the near side harder. It pulls the far side less. Over time, that difference can elongate the planet, making it more like a droplet or lemon than a perfect globe. This is not a decorative detail. It is the visible logic of proximity. The planet's outline becomes a record of the force acting on it. Like ocean tides on Earth, but lifted into an extreme world, the distortion shows that gravity can be felt across a body, not merely at its center. The comparison is gentle, but the physics is severe. Earth's tides raise water by meters. Here, the whole world answers. Then there is the atmosphere. The word atmosphere usually suggests air-sky weather clouds, perhaps blue light or haze. Around PSR J2322-2650b, the word has to be handled carefully. This atmosphere is not a breathable envelope and not a sign of life. It is a hot, irradiated, chemically unusual layer whose light can be studied from far away. Its carbon-rich signal is not a scenic claim that the world rains diamonds in view of a telescope. It is a spectral clue. Webb reads light, and light carries fingerprints of molecules and temperature. When the planet shows molecular carbon, the human-scale translation is not a jeweled sky. It is more like hearing an unfamiliar instrument in an orchestra where familiar instruments have gone quiet. The atmosphere is playing a chemical note that ordinary exoplanets rarely allow to stand alone. That is the pressure point. The atmosphere's strangeness becomes more vivid when compared with familiar planetary chemistry. On Earth, carbon is everywhere, but rarely alone. It is in carbon dioxide, in rocks, in life, in oceans, in the exchange between air and ground. On giant planets, carbon may appear in methane or other molecules. In hot exoplanet atmospheres, carbon often competes with oxygen in carbon monoxide or carbon dioxide. But PSR J2322-2650b appears to show molecular carbon in a regime where oxygen and nitrogen are surprisingly limited. The comparison is not exact because this planet is nothing like Earth-Jupiter or a normal hot Jupiter. Still, the difference helps. It is not that carbon itself is exotic. It is that carbon seems unusually free. In chemistry, freedom often means something else is missing, removed, hidden, or unable to dominate. A simple human image is a room after most of the furniture has been taken away. The chair that remains is not strange because chairs are rare. It is strange because it stands alone where a full room was expected. The carbon in PSR J2322-2650b's atmosphere feels like that remaining chair. It may not reveal the entire house, but it tells us the room has been altered. Something about the planet's formation stripping interior separation, or atmospheric loss has changed the expected mixture. The planet is not merely carbon-rich as a label. It is carbon-rich in a way that makes absence as important as presence. What is missing becomes part of the evidence. This is the micro-payoff of bringing the system down to human scale. The mystery is not only enormous, it is precise. A year shorter than a night tells us the orbit is extreme. A city-sized dead star tells us the host is compact but powerful. A stretched planet tells us tides matter. A carbon-rich spectrum tells us chemistry has departed from the expected script. Each scale bridge turns abstraction into pressure. The system stops being a distant oddity and becomes measurements that can be held in sequence. Close orbit, dense host, deformed world, strange atmosphere. Together, they form a planet that is not impossible, but instructive. It teaches that survival near a dead star is not simple. It is a negotiation between gravity, heat, radiation, chemistry, and history. But once the system can be felt, the next layer appears beneath it. These forces are not random. They belong to stellar evolution, compact remnants, atmospheric physics, and planetary identity. To understand PSR J2322-2650b, the story must move from human scale back into system scale, where the carbon world becomes one piece of a machine. The system beneath PSR J2322-2650b is not one system, but several systems folded into one another. There is the Pulsar, a compact remnant spending rotational energy through beams and particle winds. There is the planet or planet mass companion moving so close that tides stretch its body and heat may be redistributed through powerful atmospheric flow. There is the orbit short enough to repeat the same forcing in less than 8 hours. And there is the chemistry where carbon appears too prominent and other expected elements seem too quiet. At first, these pieces can be described separately: a dead star, a close world, a strange atmosphere. But the deeper mechanism is that none of them is separate. The orbit shapes the heating shapes the winds shape the spectrum reveals chemistry. The chemistry points backward toward formation. This is where the planet becomes a machine made of clues. The old instinct is to ask what the planet is, as if a single category will settle the matter. Gas giant, stripped core, pulsar companion, carbon world. Each label is useful, but each one freezes a moving story. PSR J2322-2650b is better understood as a process caught in the act. Its present atmosphere is not only a possession, it is an outcome. It reflects material that may have been inherited, exposed, separated, lost, heated, and stirred. Around a normal star, atmospheric science often begins with the balance between stellar light and planetary gas. Around this pulsar, the balance is sharper. The host is compact and extreme. The planet is close and deformed. The energy arriving from the neutron star may not behave like steady sunlight. The atmosphere must answer to a forcing pattern that belongs to a dead star still acting on its surroundings. That is the hidden system beneath the mystery. One important layer is orbital forcing. A world in such a tight path cannot ignore its host for any part of the orbit. The short year means that conditions repeat quickly, and if the planet is tidally locked, one hemisphere may face the pulsar more persistently than the other. The heated side and cooler side become part of a circulation engine. Air or gas, in the broader planetary sense, moves because pressure differences demand motion. Heat tries to spread. Molecules are carried away from where they formed and into regions where they may break, condense, or radiate differently. If winds are strong and organized, the brightest region may not sit exactly where the simplest model would place it. The planet's light then becomes a moving map, not merely a temperature reading. The image is not enough. The spectrum must be read through dynamics. Another layer is atmospheric escape and erosion. High-energy radiation and particle winds can strip lighter gases, energize upper layers, and change what remains visible. This does not mean the pulsar explains everything by destruction alone. Destruction is rarely so neat. If material is removed from the top of an atmosphere, deeper layers may become more important. If gases are lost at different rates, composition can shift. If irradiation changes molecules faster than circulation can replace them. The observed spectrum may represent a balance between creation and removal. The atmosphere becomes less like a sealed room and more like a shoreline under constant weather. What Webb sees is the present edge of that shoreline, not necessarily the untouched interior of the planet. The carbon clue sits inside this larger machinery. Molecular carbon does not only say that carbon exists, it says that the chemical environment allows carbon-bearing species to leave a strong mark. That can happen only if the surrounding conditions and elemental inventory cooperate. If oxygen were abundant in the relevant layers, carbon would often be drawn into oxygen-bearing molecules. If nitrogen were abundant in the relevant chemistry, other pathways would compete. So the carbon signal becomes a constraint on the whole system. It presses on formation models because the original material matters. It presses on interior models because deeper layers might feed the atmosphere. It presses on escape models because loss can change what remains. It presses on circulation models because winds decide where gases are seen most clearly. A single molecule becomes a messenger from the entire machine. This is why PSR J2322-2650b matters to more than the study of one planet. It forces different branches of astronomy to speak to one another. Pulsar timing gives the orbit and mass constraints. Neutron star physics describes the compact host and its energetic output. Atmospheric spectroscopy reads the planet's emitted light. Planetary dynamics describes circulation, heating, and deformation. Stellar evolution asks how such a companion could exist after collapse or stripping. No one branch can finish the explanation alone. The system is an intersection, and the intersection is the discovery. A human comparison is a clock tower standing beside a furnace, beside a wind tunnel, beside a chemistry lab, all built on the ruins of a former city. The clock tells time. The furnace supplies heat. The wind tunnel moves air. The lab changes molecules. The ruins remember an older history. Studying only one of them gives a partial answer. PSR J2322-2650b demands that all of them be considered at once. The micro payoff is that the carbon world is no longer just an odd object. It is a coupled system. Its atmosphere is shaped by where it orbits, how fast it moves, what it has lost, and what it may still be bringing upward from within. This does not solve the origin. It clarifies why the origin is hard. The present-day planet is not a clean fossil from one event. It is a living equation of forces, even if the star it orbits is dead. And that leads to the unresolved edge. When the machine is this interconnected, which part of the answer is still missing? And what does science still not know about the carbon world near the pulsar? The hardest unknown in PSR J2322-2650b is not whether the planet is strange. That part is already measured in several different ways. The orbit is extreme. The host is a millisecond pulsar. The atmosphere appears rich in helium and molecular carbon. The system sits at the edge of known exoplanet categories. The harder unknown is how all of those facts became true at the same time. A mystery becomes sharper when its pieces are clear, and here the pieces are clear enough to resist easy arrangement. The planet exists close to a dead star, but existence does not explain origin. The spectrum suggests unusual chemistry, but chemistry does not automatically reveal the path that produced it. The shape may be stretched by tides, but shape does not tell the full history of mass loss heating or internal structure. The clock gives the orbit. Webb gives the atmosphere. The missing thing is the story that connects them. That is the unresolved edge. Scientists can model a normal hot Jupiter, even if the details are difficult. They can model a stripped companion, even if the history is complex. They can model atmospheric escape, irradiation, circulation, and chemical reactions. But PSR J2322-2650b asks for those models to work together in a region where there are few examples for comparison. A single system can be studied deeply, but it is hard to know which features are universal and which are accidents. If 10 similar pulsar planets were known with measured atmospheres, patterns might emerge. Some would be carbon-rich, some would not. Some would orbit closer, some would show different winds. But with one object like this, every clue is both precious and dangerous. It may represent a class. It may represent an exception. It may represent a short-lived stage that astronomers happened to catch because the geometry allowed it. The uncertainty is not weakness. It is the honest shape of the evidence. One unresolved question is whether the atmosphere reflects the planet's birth or its damage. If the carbon-rich chemistry comes from formation, then the material that built the companion was already unusual. Perhaps the system began with a disk or companion history that concentrated carbon in a way ordinary planet formation does not. But if the chemistry comes from damage, then the present atmosphere may be a processed remnant, what is left after radiation escape and internal separation removed or hid other elements. These two interpretations can lead to very different stories while producing the same broad phrase, carbon-rich atmosphere. One story says the planet was born strange. Another says it became strange. The evidence has not yet fully chosen between them. Another question is where the missing oxygen and nitrogen have gone. They may be genuinely scarce in the observable layers. They may be locked deeper inside. They may have been lost to space. They may exist in forms that are not easy to detect under the present conditions. They may be hidden by temperature structure clouds, opacity, or the limits of the model. This is where a spectrum becomes both powerful and incomplete. Light reveals what interacts with it. It does not reveal every atom in every layer. An atmosphere is not a flat sheet. It has depth, pressure, motion, and temperature. Webb can read the light emerging from the system, but translating that light into a complete chemical inventory requires models, assumptions, and careful tests. The measurement is real. The interpretation still has layers. A third unresolved question concerns time. How long has PSR J2322-2650b looked this way? Is the carbon-rich atmosphere an ancient stable condition lasting for millions or billions of years? Or is it a temporary stage in a slow erosion process? A planet near a pulsar is not frozen in one state. It can lose gas. It can cool. It can be heated unevenly. Its interior can evolve. Its orbit can change subtly. The atmosphere seen now may be the current chapter of a much longer transformation. This matters because the same object can have different identities across time. A companion that began as a star-like object might become a stripped remnant. A remnant might acquire or expose a strange atmosphere. A strange atmosphere might later be lost. The planet is not just a thing. It is a phase. This makes the system feel less like a specimen in a cabinet and more like a frame from a long film. One frame can be clear, but it cannot show the whole motion. The frame tells astronomers what is visible now: a close orbit, strong irradiation, molecular carbon, an unusual companion. To reconstruct the film, they need physics that can move backward and forward. They need to test whether a black widow-like pathway can produce the observed composition. They need to test whether second-generation formation can build something this massive and close. They need to test whether atmospheric loss can remove oxygen and nitrogen efficiently enough. They need to test whether deep carbon-bearing material can be mixed upward. Each test is a bridge from the present measurement to the hidden past. Some bridges will fail. That is useful too. The micro-payoff is that the unknowns are no longer vague shadows. They have names, origin-missing elements, atmospheric lifetime interior structure, wind dynamics, and the scarcity of comparison objects. PSR J2322-2650b is not unexplained in the empty sense. It is unexplained in the rich sense, where every answer must pass through several measured constraints. That is why the planet matters. It is a locked door with the outline of the key already visible. The orbit sets one tooth of the key. The pulsar sets another. The spectrum cuts a third. The atmosphere's carbon richness makes the final shape difficult. The next step, then, is not louder speculation. It is better instruments, better models, and more patient ways of asking the same question from different angles. To understand the carbon world, science must find out whether Webb has seen a rare survivor, a stripped remnant, a rebuilt object, or a temporary atmospheric stage. And that brings the story naturally toward the next method, because the mystery will not be solved by naming it. It will be tested by watching light, time, and theory meet again. The next test of PSR J2322-2650b will not be a single heroic photograph. It will be a slow tightening of several kinds of evidence. That matters, because the planet has already shown the danger of relying on one mental image. It is easy to imagine a dark carbon world beside a flashing neutron star, stretched by tides and wrapped in a strange atmosphere. The image is useful, but the image is not the measurement. The measurement comes from timing spectra. Brightness changes models, and the careful refusal to let any one clue explain more than it can. To move from mystery toward understanding, astronomers have to ask the planet the same question in different languages. The clock asks where the companion is and how it moves. The infrared spectrum asks what the atmosphere is doing. The light curve asks how heat is distributed around the orbit. The chemistry models ask which molecules can survive. No one test is enough. The next method is convergence. The first path forward is more refined spectroscopy. Webb has already opened the atmosphere by measuring infrared light across the planet's orbit. But an atmosphere is not a flat label. It has vertical layers, pressure regions, temperature differences, and changing visibility depending on wavelength. A spectrum can be made sharper by covering more wavelengths, by reducing uncertainty, by observing at different orbital phases, and by comparing the data with more realistic models. If carbon-bearing molecules dominate future spectra, can test whether the same signatures remain stable, whether other weaker species appear, and whether clouds, haze, or temperature structure are disguising part of the chemical inventory. The goal is not merely to confirm that carbon is present. The goal is to ask how carbon is arranged, where it is visible, and whether the missing elements are truly absent or only hidden from the particular layers Webb can read. The second path is phase curve mapping. A distant planet cannot be resolved into continents or storms, but as it orbits, different hemispheres face the telescope. The combined infrared light rises and falls. That changing brightness can reveal where the hottest region sits, how efficiently winds carry heat, and whether the atmosphere is shifted by circulation. On a normal, hot Jupiter, such measurements can show whether winds move energy eastward or westward from the dayside. On PSR J2322-2650b, the same idea enters a stranger environment because the host is a pulsar, and the rotation, irradiation, and tidal distortion are extreme. If the hottest region is displaced from the simple subpulsar point, the displacement becomes a clue about wind direction and atmospheric motion. A light curve becomes a weather map drawn with almost no pixels. This is where patience becomes an instrument. Another path is better modeling of atmospheric escape. A planet so close to a pulsar may lose material under high-energy radiation and particle bombardment. But escape is not just a yes or no process. Different gases can escape differently. The upper atmosphere can be heated, lifted, ionized, and stripped. Material leaving the planet may form a faint flow around the system, possibly interacting with the pulsar wind. If models can predict which elements should be lost fastest, and under what conditions, they may explain whether oxygen and nitrogen could be removed from the observable atmosphere while carbon remains prominent. Or they may show that escape alone is not enough. Either result would be useful. A failed explanation is not wasted. It narrows the corridor. Interior models are another quiet but important test. If the planet or companion contains carbon-rich layers beneath the atmosphere, scientists must ask how that material reaches the observable region. Cooling, crystallization, differentiation, mixing, and erosion could all matter, but each has to obey thermodynamics and structure. The idea that carbon crystals might form under certain conditions can be evocative, but it cannot be used as decoration. The real scientific question is whether interior separation could plausibly create a carbon-rich outer layer, while oxygen and nitrogen remain hidden, removed, or chemically unavailable. That question requires models of pressure, temperature, composition, and time. It also requires humility, because the interior cannot be seen directly. The atmosphere is the messenger, and messengers can carry only part of the story. Timing will also remain essential. The pulsar is still a clock, and continued timing can refine orbital parameters, search for subtle changes, and constrain the mass and geometry of the companion. A tighter orbit solution helps every other model, because atmosphere and formation depend on distance, inclination, heating, and tidal effects. In a system like this, even small improvements matter. A slightly better angle can change the inferred size. A better mass constraint can change whether the object feels more like a giant planet or a stripped remnant. A better orbital model can show how close the companion is to filling its Roche lobe, the region where gravity begins to let materials spill away. The clock does not reveal carbon, but it defines the stage on which carbon is observed. The largest future test may be comparison. One object can be understood deeply, but a population gives science pattern recognition. If surveys find more pulsar planets or planet mass companions with measurable atmospheres, PSR J2322-2650b PSR J2322-2650b can stop being a solitary riddle and become the first member of a class. Perhaps other pulsar companions will also be carbon-rich. Perhaps they will show helium-oxygen metals or different molecular signatures. Perhaps some will fit Black Widow expectations and some will not. That comparison would decide whether this carbon world is an exotic exception or a clue to a broader evolutionary route. The micro payoff is that the mystery has a practical future. It does not depend on one dramatic discovery that must solve everything at once. It can be approached through repeated spectra phase, curves, timing escape models, interior physics, and the search for cousins. Each method tests a different seam in the same fabric. Some will confirm parts of the present picture. Some will weaken favored ideas. Some may reveal that the atmosphere is even more layered than it first appeared. The next question is therefore larger than technique. If better instruments and models can turn this planet from anomaly into evidence, what does that evidence do to the wider understanding of planet stars and the strange afterlives of stellar systems? PSR J2322-2650b matters because it changes where planetary science has to look for planets. Not toward comfort, not toward habitability, not toward blue skies or familiar worlds, but toward the afterlife of stars. A planet around a living star already carries history. Its orbit remembers the disk where it formed. Its atmosphere remembers heat loss, chemistry impacts, and migration. But a planet around a pulsar carries another chapter entirely. Somewhere in its past, the central star crossed the boundary between ordinary stellar life and compact remnant. Matter collapsed. The system was rearranged. Radiation, gravity, and time took on new forms. Yet a planet-mass body remains close to the remnant, and its atmosphere now holds a chemical clue that does not fit easily into the oldest expectations. The consequence is quiet but large. Planetary evolution does not end when a star dies. In rare systems, death becomes another environment. This changes the emotional scale of exoplanets. Most worlds are described through comparison with the solar system. A hot Jupiter is like Jupiter moved inward. A super-Earth is larger than Earth, but smaller than Neptune. A mini-Neptune suggests a small gaseous world. Even strange planets are often made understandable by borrowing familiar names. PSR J2322-2650b resists that habit. It has a Jupiter-like mass, but not a Jupiter-like setting. It has an atmosphere, but not one shaped by a normal sun. It has an orbit, but the host is a rapidly rotating neutron star. The familiar comparisons help only briefly, then fall away. What remains is a broader category: planetary bodies as survivors, remnants or products of extreme stellar histories. That category is not comfortable. It is more interesting because it is not comfortable. The larger consequence begins with formation. If PSR J2322-2650b formed before the neutron star, then planets can survive or be reworked through events that would seem to erase ordinary systems. If it formed after the neutron star, then planetary formation can happen in environments far removed from young solar disks. If it was stripped down from something larger, then some planets may not be born as planets at all, but become planetary through loss. Each possibility changes the meaning of origin. A planet may be a first-generation world formed with its star. It may be a second-generation world assembled from leftover or returned material. It may be an exposed remnant reduced into a planetary mass by a compact host. The word planet describes the present body. It may not describe the beginning. This is where PSR J2322-2650b becomes more than a rare object. It becomes a warning against assuming that categories contain histories. Two planets can have similar masses and completely different pasts. Two atmospheres can have similar temperatures and completely different chemistry. Two close orbits can arise from different routes through time, around ordinary stars. Exoplanet science already learned this lesson many times. Around dead stars, the lesson becomes sharper because the violence of the host is part of the archive. The planet is not simply orbiting a remnant. It is part of the remnant's story, and the remnant is part of the planet's chemistry. The system cannot be cut neatly into star and planet cause and consequence. It is a coupled afterlife. A human-scale image may help. Imagine a shoreline after a storm that has lasted centuries. The cliffs have been carved back. Old foundations are exposed. New sediment has been laid down where streets once stood. A visitor can still call it a shore, but the word shore does not tell which stones are ancient, which were carried in, and which were broken from the cliffs yesterday. PSR J2322-2650b is like that shoreline. The atmosphere Webb reads may contain original material, processed material, exposed interior material, or the residue of gases lost over time. The carbon signal is one visible layer of a much longer reshaping. The world is not only an object, it is a record. The consequence for atmospheric science is equally important. Webb has shown that exoplanet atmospheres can be studied in stranger places than the classical planet-star picture. Because the pulsar is not bright in the infrared in the same way as a normal star, the planet's own emission can become unusually accessible. That turns the system's strangeness into an observational advantage. A dead star that would seem hostile to planets can also make one planet easier to read. The absence of ordinary starlight becomes part of the method. In that sense, PSR J2322-2650b is not only a challenge to formation theory. It is a demonstration that extreme systems can open observational doors that calmer systems keep closed. The broader consequence reaches into the meaning of survival. Survival does not require gentleness. It does not require an Earth-like path. It does not require a stable main-sequence star shining for billions of years. Survival can mean remaining bound after catastrophe, being stripped into a new identity, or carrying an atmosphere that only makes sense after prolonged damage. This is not comforting, and it should not be made sentimental. It is simply a deeper form of continuity. Matter persists. Orbits persist. Chemistry persists, but not unchanged. The universe does not preserve worlds like museum pieces. It alters them sometimes beyond recognition, and then leaves enough evidence for a telescope to read. The micro payoff is that PSR J2322-2650b widens the story of planets from birth to afterlife. It shows that dead stars can still shape planetary bodies, not as warm parents, but as compact engines of force. It suggests that the strangest worlds may not be exceptions outside planetary science, but boundary cases that reveal what the word planet has been hiding. The central question is no longer only how a planet can survive so close to a pulsar. It is what survival means after a star has died and the system has been remade. That opens the final quiet turn, because once the science has widened the object, itself begins to feel different. The carbon world is not merely a curiosity. It is a reminder that the universe keeps rewriting familiar names long after their first meanings seem settled. The quiet philosophical turn in PSR J2322-2650b begins with a definition that still works and an intuition that does not. By definition, the object is a planet because it has planetary mass and orbits a stellar remnant. That classification is useful. It keeps the science grounded. It prevents the story from drifting into fantasy or turning every strange object into a new category before the evidence demands it. But the word planet carries a hidden warmth from human experience. It suggests a world beneath a star, a place that belongs to a solar system, an object formed from a disk and aged under light. PSR J2322-2650b keeps the word while draining it of comfort. It is a planet around a dead star. It is close enough to be deformed. It carries an atmosphere that seems rich in carbon and helium, not the familiar mixture expected from ordinary gas giants. The name remains. The meaning becomes colder. That does not make the object less real. It makes it more revealing. Science often advances when a familiar word survives contact with an unfamiliar case. Star once meant a point of light in the sky, then became a physical body with mass temperature, nuclear burning magnetic fields, and death. Planet once meant a wandering light, then became a category of worlds with geology atmospheres, rings, moons, and migration histories. Now the word stretches again, not because PSR J2322-2650b breaks the rules, but because it occupies a place where the rules expose their own limits. A planet can orbit something that no longer shines like a sun. A planet can be shaped by a star after that star has died. A planet can be understood through timing and spectra before it is ever imagined as a surface. The category holds, but the imagination must be rebuilt around it. This is where the story becomes less about rarity and more about perspective. Most planetary thinking is shaped by the solar system because it is the first example available to human senses. Earth has a bright star, a stable orbit liquid, water, a layered atmosphere, and a sky that makes the sun feel generous. Even the other planets are organized around that same central light. But the galaxy does not owe its planets a solar system shape. It builds worlds around red dwarfs, swollen stars, binary stars, white dwarfs, and in rare cases, pulsars. Some worlds are born in calm disks. Some may be rebuilt from debris. Some may be carved down from larger companions. Some may survive only as altered bodies carrying a history that would be invisible if astronomers insisted on familiar origins. The universe does not begin with categories. Categories come later after measurement. There is a humility in that order. The measurement comes first. The meaning follows more slowly. PSR J2322-2650b also changes the emotional meaning of dead stars. A dead star sounds like an ending, and in one sense, it is. Fusion has stopped. The long stellar life has closed. The massive star that once existed is gone. Its outer layers thrown away, its core collapsed into a neutron star. But the system is not simply over. The remnant spins. Its beams sweep space. Its gravity holds a companion. Its radiation and particles shape an atmosphere. Death, in this astrophysical sense, is not silence. It is transformation into a different kind of activity. The dead star does not nurture a planet. It imposes itself on one. It does not give the gentle continuity of sunlight. It gives a harsher continuity of force. That distinction matters because it keeps awe from becoming sentimentality. There is nothing cozy about this system. Its beauty is severe. A useful human comparison is not a garden after winter, but a clock still running in the ruins of a burned observatory. The building has changed beyond recognition. The roof is gone. The walls are scarred. Yet some mechanism remains marking time in the dark, and around that mechanism another object still moves. The motion does not undo the disaster. It records what survived it. PSR J2322-2650b is that moving record. It does not tell a story of safety. It tells a story of persistence under altered conditions. The planet is not protected from the dead star's past. It is defined by it. Its orbit, atmosphere, and possible origin all carry the imprint of a system that has passed through violence and continued into a stranger form. This is why the philosophical turn must stay precise. The planet does not prove that life can thrive around pulsars. It does not turn carbon chemistry into destiny. It does not make dead stars friendly. What it does is more subtle. It shows that the boundary between ending and continuation is not simple in astronomy. A supernova can erase one kind of system and prepare the conditions for another. A stellar remnant can be both corpse and engine. A planet can be both survivor and transformed object. A spectrum can be both a present measurement and a clue to a hidden past. In that layered meaning, PSR J2322-2650b becomes a reminder that the universe is not organized around human emotional categories. Dead can still be active. Small can still be massive. Dark can still be measurable. Strange can still be lawful. The micro payoff is a changed intuition. The listener no longer sees the carbon world as a bizarre exception beside a dead star, but as a boundary where familiar ideas become more accurate by becoming less comfortable. The science is not diminished by uncertainty. It is sharpened by it. The planet's atmosphere remains unresolved, yet the unresolved part is exactly what gives the system its depth. It asks for better models, not louder claims. It invites wonder without surrendering caution. And now the story can return to where it began, a planet circling a dead star in less than a night. At first, that image seemed impossible to place. After the journey through timing, pulsars, chemistry, tides, winds, and origin, it becomes something clearer and stranger. It is not a violation of planetary science. It is planetary science at its far edge, where the final synthesis can begin. PSR J2322-2650b began as a contradiction, a planet circling a dead star so closely that its year is shorter than an ordinary night. At the beginning, that image seemed almost unstable. A world should not feel natural beside a pulsar. A planet should not seem at home around the collapsed core of a massive star. A Jupiter mass body should not sit so near a neutron star that tides pull it away from roundness, while its atmosphere speaks in the strange chemical language of helium and molecular carbon. Yet the deeper lesson is not that the system violates nature. It is that nature has more ways to make and remake worlds than the familiar solar system first suggests. The orbit is real. The star is dead. The planet remains. The atmosphere is not familiar. That sequence is the final shape of the mystery. The first answer to the central question is simple enough to say quietly: a planet can survive close to a pulsar because gravity still binds systems after stellar death. A neutron star may be the remnant of catastrophe, but it is still massive. It still holds companions. Orbits can remain change titan or be rebuilt through histories that are difficult but not outside physics. The body called PSR J2322-2650b moves around the pulsar because the old rule still applies in an extreme place. Mass curves space. A companion follows. But this answer is only the flaw of the story. It explains motion, not origin. It explains why the planet can be there now, but not how it came to be there, why it has this atmosphere, or why the chemistry appears so different from ordinary exoplanets. Survival is the beginning of understanding. It is not the whole understanding. The second answer is stranger. The planet's atmosphere may look unusual because it is not simply the atmosphere of a normal planet placed near a harsh star. It may be the visible result of a long sequence of forcing stripping heating circulation and internal history. The pulsar bathes the companion in high-energy conditions. Tides distort the body. Winds may carry heat and molecules across a rapidly forced atmosphere. Material may be lost, mixed, exposed, or chemically sorted. The carbon-rich spectrum is therefore not a decorative label. It is a clue to an altered system. Carbon seems to stand out because the expected competitors, especially oxygen and nitrogen in the observable layers, do not appear to dominate in the familiar way. The important thing is not carbon alone. The important thing is the whole imbalance. The atmosphere is strange because something in the planet's past or present has made that imbalance visible. That is why the old categories remain useful but incomplete. If PSR J2322-2650b was once a normal giant planet, then its present closeness and chemistry need explanation. If it was once a larger companion stripped down by the pulsar, then the carbon-rich atmosphere must still be accounted for. If it formed after stellar death, then the source material and formation pathway must be found. If the truth is hybrid, then the planet is not one story, but several chapters compressed into one object. A body may begin as one thing and end as another. It may become planetary by losing mass. It may carry an atmosphere that no longer resembles its birth. It may be both survivor and remnant, both planet and archive. The word planet remains correct, but it no longer feels simple. It has absorbed history. The deepest payoff is that PSR J2322-2650b does not make the universe less orderly. It makes the order less familiar. The planet does not prove alien life. It does not prove unknown physics. It does not confirm a world of falling diamonds, even if carbon-rich interiors allow evocative possibilities under certain conditions. Its importance is quieter. Webb has read light from a companion near a pulsar and found a chemical regime that challenges comfortable formation stories. Pulsar timing revealed the orbit. Spectroscopy opened the atmosphere. The shape and proximity revealed the force of the host. Each measurement took one step away from imagination and toward evidence. The final mystery survives not because science failed, but because the evidence became good enough to make the easy answers inadequate. There is a kind of beauty in that. A weak measurement can create vague wonder, but a strong measurement creates exact uncertainty. PSR J2322-2650b is now uncertain in an exact way. Its orbit is known enough to be astonishing. Its host is understood enough to be severe. Its atmosphere is measured enough to be chemically disruptive. Its origin is unresolved enough to matter. The world is no longer a rumor in the dark. It is a defined problem with edges. The carbon world has become a question that can be returned to with better spectra, better models, and perhaps one day with other pulsar planets for comparison. The door is not closed. It has finally opened wide enough to show how much is still inside. So the final image changes. At first, it was a planet trapped beside a dead star, a cold and strange picture at the edge of plausibility. Now, it is something more precise, a planetary mass body moving through the afterlife of a star shaped by a compact remnant that no longer burns like the sun, but still spends energy, still marks time, still sculpts matter nearby. The planet's atmosphere is not an ornament around the story. It is the story made visible in infrared light. It tells of carbon where familiar chemistry expected other voices of survival, where stellar death should have erased easy explanations of categories that remain useful only when they are allowed to stretch. PSR J2322-2650b does not answer every question it raises. It gives a better question. How many other worlds have been transformed by dead stars, waiting not in bright images, but in timing shifts and faint spectra? The carbon world keeps orbiting. The pulsar keeps turning. And between them, in the darkness after stellar death, a planet continues to show that the universe can preserve a mystery without breaking a single law. In the end, PSR J2322-2650b remains less like an answer than a threshold. It shows that a planet can exist where the mind expects only aftermath, and that a dead star can still shape matter with gravity, radiation, and time. The pulsar at the center no longer burns with the long patience of a normal star. It spins it, beams it, marks the dark with pulses, and beside it a world continues its short orbit, completing year after year in the span of a single night. That motion is not gentle. It is a record of survival under pressure. The planet may be a survivor, a remnant, a transformed companion, or some layered result of histories not yet fully separated. Its atmosphere does not offer a final confession. It offers carbon-helium heat motion and absence. It offers a chemistry that turns the familiar word planet into something colder, stranger, and more precise. This is what makes the system worth remembering. Not because it is impossible, not because it proves a hidden miracle, but because it shows how far ordinary physics can go when the setting becomes extreme. Gravity still binds, light still carries fingerprints, matter still changes under force, a spectrum still opens a door. And beyond that door is a larger thought. The universe does not stop making planetary stories when stars die. Some stories continue in ruins. Some are carved down. Some are rebuilt. Some are only visible when a telescope learns how to listen to a clock and read the faint warmth beside it. The carbon world keeps circling. The dead star keeps turning. And between them, in the cold machinery of a remade system, science finds not an ending, but a quieter and stranger beginning.